next speaker is Brian Axelrod.
Hi, I'm going to talk. Oh, can you hear me now? Okay. I'm going to talk to you about sample amplification, increasing data size even when learning is impossible. And this is joint work with Shivam Garg, Vatsal Sharan, and Gregory Valiant at Stanford. And the paper is also on arXiv if you want to go and take a look. So let's introduce the context first. So say I have some sort of distribution over paintings, and you want to buy 10 paintings that are sampled ID from such said distribution. And each sample costs, say, $100. Now, you go ahead and you ask me, your grad student, to buy you 10 paintings, and you give me $1,000. But what if I want to steal $100? Can I go buy 9 paintings and amplify them to produce 10 paintings that are indistinguishable from 10 draws ID from D? And is this possible even if 9 samples is not enough to learn the distribution D? So our goal, kind of a little bit more formally, is going to be to generate a data set of size M that's going to be indistinguishable from N independent draws from the distribution D. And one thing that we really want to understand is how much do we actually need to learn about D? Do we actually need enough samples to learn D, or can we do better? And you can always ask, is there a connection to GANs? Suppose a system can accomplish such a task, kind of what does that mean in terms of the information it's actually acquired? So let's kind of state all this a little bit more formally. We're going to formalize this as a game with 2 players. On one hand, we're going to have the amplifier, which is going to take in N ID samples from D and output M, hopefully more than N samples. And on the other hand, we're going to have the verifier that's going to take M samples, and it's going to output an accept or reject. And the goal of the amplifier is going to output M samples that all verifiers accept with high probability. Kind of with the condition a useful verifier has to accept samples that actually were drawn ID from the distribution. And something to note, it's the verifier actually knows the true distribution D, whereas the amplifier does not. And there's also an equivalent definition in terms of total variation distance on the distribution of like M samples ID from D. So, and just going to give you a brief preview of the results because actually presenting the proofs isn't going to fit in 5 minutes. But how many samples does it take to learn a distribution over k elements? You guys should know this. Anyone? Okay, very good. Order k. And then how about a d-dimensional multivariate Gaussian with known covariance? How many samples roughly does that take, just in terms of dimension d? D, great. And we're going to find that it's actually much easier to increase the data set size by only 1 point. In the case of a distribution over k elements, it only takes order square root k elements before we can generate an additional point. And likewise, with a d-dimensional Gaussian, it only takes order square root d. So, and you can go a little bit further. So what are our results going to actually look like? Well, for the class of discrete distributions with support at most size k, we can take an amplification procedure that takes n input samples and outputs n plus order n over square root k samples. Right? So in some sense, if I'm able to amplify and you double the amount of samples that you give me, I can produce double the amount of new samples. And then for the class of d-dimensional Gaussian distributions with unknown mean, known covariance, we can do the same thing, just replace the k with a d. And if you go out and read the paper, you'll notice that the algorithms actually look quite different. You can do something reasonably naive in the case of discrete distributions, but you actually have to do something quite a bit more clever for the d-dimensional Gaussians. Okay. Any questions? Yes, but there's probability, so the total variation distance will add then. Yeah, you can't sadly break all the statistical lower bounds this way.
Oh, let's thank the speaker again.